Hello and welcome, everyone. Nice to see you. Thanks for coming to the talk today. We're going to be talking about don't build a distributed monolith for the next hour. I'm going to help you hopefully avoid all these mistakes that commonly lead to a distributed monolith when you're trying to build microservices. I want to start out with a story. Recently, a client came to us at Trailhead and said, we've just finished a very well-organized and architected microservices architecture, and the application is just about to launch, but we have just a couple of small problems with the application that we'd like you to look at. They're performance-related, but if you could take a look at those two small issues and then help us launch the application, we'd really appreciate it. Well, it didn't take us long of looking at their code and their architecture to figure out they had not actually built microservices. They had built something called a distributed monolith. And we're going to be talking about what that means today. But it's far from the only time that a client has come to us with something that they aimed at microservices that became a distributed monolith. And that's the reason that I created this talk. I wanted to share the common mistakes that we saw at Trailhead with all of our clients that came in with these distributed monoliths and how we believe they got to that point so that you can build your own microservices while avoiding these same mistakes. So I'm going to talk through the 10 most common mistakes that I've seen from all of our clients and prospective clients. Before we get started, just a little bit about me. My name is Jonathan Tower. I go by Jay for short, so if we get a chance to chat afterwards or around the conference, feel free to call me Jay. I'm a partner and principal consultant at Trailhead Technology Partners. We're a custom software consulting firm. We've been in business just about 10 years. I've also been a Microsoft MVP in .NET 10 times in a row, looking to get renewed, hopefully, for an 11th time in July. You can contact me at all these places online if you're interested in connecting afterwards. You'll also notice at the bottom of the slide I have a link to GitHub where you can get all of the slides that we're going to be looking at together today. And then the last thing on this slide is something I like to offer to anyone that comes to one of my talks. This is an expert consultation. If you're looking for a time on my calendar to chat with me, even though I'll be in the US and you'll probably be in Europe, we can find a time that'll overlap. You can ask questions that you maybe don't want to ask in front of everybody else. Maybe you need me to sign an NDA before I can look at your code and you can show me something specific. Or I've even had people contact me using this link to say, I really liked your talk. My team really needs to see the same talk. Will you do it for us? So feel free to use that QR code or bit.ly link for whatever purpose you find useful. All right, so let's start out the talk today with some definitions. First of all, what is microservices? What is a monolith? What is a distributed monolith? We'll start with a monolith. This is something that hopefully all of us are probably already familiar with. This is the traditional approach to software development, where you have a single artifact that you produce, usually through a single build, and usually deploy it to a single location. There's lots of advantages and disadvantages to these. You may already be familiar with those from using them. We're going to go into a lot of detail on those today. This is what an architecture diagram might look like for a basic web application that is a monolith. You'll notice it's got just this one column. That's kind of why we call it a monolith. So there's the application layer, and then there's a database or a data store. And then we've got our clients fanning out above there. Now, of course, we know for years that monoliths are scalable. There's different ways to do it. One of them is what we would call scaling out or horizontal scaling. That would be adding more resources to the application server, making more processors, more powerful VM, more storage, faster network connection. And then the other one would be also horizontally scaling the database, making that more resource rich. You can also scale out. This is when you add multiple instances of things. So load balancing a web application, for example, would be a common way to do this. Or to use Azure terminology, having multiple instances of your app service running, right? You can do the same thing with the database through architectures such as data sharding, where you take your data and you split it up into what are called shards. And organize that data around some sort of a key. Maybe it's a client ID or a user ID or something where it's okay for that data to be split on, and you make multiple copies of your database based on that. So we've known for years that these are scalable, but I'm guessing you're in this talk partially because you also know from experience that that doesn't always mean that a monolith performs well. There's actually two different kinds of monoliths, and I want to make this distinction today because I want to talk about the good and the bad kind of monoliths. The first kind is the good kind. This is the modular monolith. This is a well-designed modular monolithic application, still deployed and built as a single artifact, potentially still very scalable through the technologies that we just talked about, but it's well organized. You can go into one part of the code and make a change. You know right where to go. The change that you make is very unlikely to break anything else. That's how you know you're editing a modular monolith. There's the other kind that I'm guessing you came to this talk because you're more familiar with, and this is commonly referred to as the ball of mud monolith. I think that's a great analogy. That's an analogy that's been around for decades. You've probably heard of spaghetti code. That's another common analogy people use for this type of monolith. This is the kind of monolith where when you go in to make a change, you need to regression test the entire application because the change you make over here might break something over here unintentionally. And when that happens a lot, you know you have a ball of mud monolith on your hands. The last architecture, or the goal architecture in a lot of cases these days, is the microservices architecture. This is an architecture and an organizational structure, and we're going to talk about that more today. But it's one that allows you to do software development that's composed of small, loosely coupled services that communicate with each other through well-defined messages. That's kind of the definition of a microservice. What does it look like architecturally? Typically, it's going to look something like this, where you'll have some sort of a API gateway layer your clients will come in through, and then the requests will get divvied out from there to different columns or services within your application. And you'll notice, importantly, all of these have their own application layer and their own data storage layer or database. And then the last layer here of a typical microservices architecture is some sort of an event bus, a way for each of these services to communicate with each other asynchronously. The last one I want to talk about is the bad guy in the story today. This is the distributed monolith. This is what I'm hoping that my talk today will help you avoid accidentally building. No one sets out on purpose to build a distributed monolith. Nobody says, this is the architecture for us, let's do this. This is always an accident, and it's always an accident built based on attempting to build microservices. This is composed usually of microservices that are accidentally highly coupled with each other and therefore become basically a monolith that's been distributed separately. This is the worst of both worlds. You get all of the problems of a bad monolith. You get all of the problems of microservices or all of the trade-offs. And you get very few, if any, of the advantages of those two architectures. So this is what we really want to avoid building. This is what a typical distributed monolith might look like. It's not dissimilar from the microservices architecture. You'll notice the big difference here, which I've highlighted in red, is these arrows between the different columns. Whether it's an application talking to a different services database or applications talking directly to each other. This is a common architecture, though a lot of times people will have been to a talk about microservices and they'll know that they need some sort of an event bus. So they'll add that event bus, but if those red arrows are still there between the services, it's very likely to become a distributed monolith. Another very popular way to create distributed monoliths is this architecture right here. I love showing this slide because I can immediately tell from the smiles in the audience who is working with this architecture right now at work. Don't worry, I won't turn you in. This is a very popular one, and I think the reason this happens is because software developers will go to a conference not dissimilar from this one. They'll learn about microservices architecture. They'll come back to the team and say, hey, everybody, let's do microservices architecture. the database administrator will start asking questions about it and say, so you're telling me that every part of the application is going to have its own data. There's going to be multiple copies of data. They won't be normalized. They'll have to synchronize with each other. Everything that I've learned as a database administrator for the last 30 years tells me that that is all terrible ideas, lots of red flags. I'm not going to let you do that. You can do whatever you want in this layer, but we're going to have a traditional, well-organized, and normalized database. That's what often I think happens. And so then the development team goes ahead and tries to make that happen. But we'll talk today a little bit more about how having a shared database like this creates coupling between your services and causes you to have a distributed monolith. So at a high level, to organize these 4 different types of application architectures that we just talked about, I would organize them on this 2-dimensional matrix, where along the bottom, we have how logically separated things are, how modular, essentially. So on the left, it would be everything is very monolithic, and on the right, everything is organized very modularly, and then physically distributed going up and down. So is it distributed as a single piece or many pieces? And so going along those lines, we have the ball of mud monolith, which is organized as a highly coupled, non-modular chunk of code and is distributed as a single piece. You have the modular monolith, or a good monolith, that is distributed as a single piece, the same as the ball of mud, but it's organized much better, more modularly. Then you have the distributed monolith, perhaps the worst of all of these, which is monolithic in its architecture. Everything is coupled to everything else in the application, but then you try and just deploy those pieces separately. And the last is the true microservice, the goal anyone building distributed monolith is actually aiming at, which is where you create modular, non-coupled modules and distribute them separately. So let's jump into the 10 most common mistakes that I see so that you can avoid creating one of these distributed monolith monsters yourself. Problem number 1 is assuming that microservices are better than a monolith. There's reasons to build microservices. There's reasons not to build microservices, like any architecture, right? The joke in the industry is that a good software engineer will answer every question by saying, it depends, right? And that's somewhat true, based on the fact that not every architecture is a good fit for every need. Sam Newman, who's written quite a bit about microservices architecture, and is a big fan, I should say, of microservices architecture, says that you should only do microservices architecture if you have, quote, a really good reason. If you don't have a really good reason, you should probably consider doing a monolith, because, in my experience, unscientific data, but just from the clients that have come to us with microservices problems, over 90% of the companies that have tried to build microservices have accidentally created a distributed monolith. That's a pretty bad failure rate, and so it's very risky, which is why Sam Newman says make sure you have a very good reason if you're setting out to build microservices. So just keep in mind, monoliths are not inherently bad. We can scale them. We can design them in a modular way that's easy to maintain. Microservices are very hard to do well, especially if your team doesn't have any experience doing microservices already. And anytime you make a mistake in doing it, you're very likely to accidentally create a distributed monolith. Some of the really good reasons I would suggest considering are if you need a lot of scalability options, if you need to be able to scale parts of your application separately from each other. If you're an airline, for example, you might want to update parts of your application, like the part that maintains people's profiles, while not impacting the part that takes reservations, because reservations is where your money comes from. If you mess that up, you're going to start losing a lot of money really fast. That would be one option. Independent deployability, having separate teams working on separate parts of the application, completely independent of each other, maybe different tech stacks. Maybe they don't really know that much about each other's parts of the application. Isolating surface area failure, I kind of mentioned an example of that already, and independent teams I talked about too. So this is, if you only remember one thing in this talk, I'd like you to remember that monoliths don't have to be bad. But if you remember two, I'd like you to remember this slide right here, which is that the trade-off that you want to keep in mind, the "it depends" answer from any good engineer with microservices is that if you want to go with microservices, you're going to get independent scalability and probably better high availability. But if you go with monoliths, you're going to get something called immediate consistency. What does that mean? That means when someone updates some data in this part of the application, the whole application will know about that update immediately. Why? Because the whole application is one thing that shares one data store. And so the application gets immediate updates throughout. When you do a microservice, you're not going to get an immediate consistency. You're going to get what's called eventual consistency. That means somebody goes in and updates some data in this part of the application. It goes to the event bus. The other parts of the application find out about it. Best case scenario, a few milliseconds. More likely, a few seconds or minutes before the whole application is consistent with that data update. So if immediate consistency sounds like something that you absolutely must have, I would say never start out building microservices. That's going to be a problem. Problem number 2 is sharing your data store or your data models. Let's start with the data store. I talked about this one a little bit when we were talking about what the typical architecture of a distributed monolith looks like, and I showed you this slide before. So let's imagine a scenario where each of these microservice applications shares the database, and let's say that the team is smart enough to know that they should at least divvy up the tables and say who owns each table, who's allowed to change each table. So this team that works on this service right here decides they need to make a schema change to one of the tables. But wouldn't you know it, all of this data is in one place, and somebody on this team over here got lazy and said, I don't want to have to listen for events and wait for eventual consistency. I'm just going to call the database and read directly from that table. I'm just reading from it. It's not dangerous, right? Well, schema change, now it is dangerous. That application, if it's not updated at the exact same time, which it shouldn't have to be if they're microservices, it's now going to be reading from a table that might have a different column name, a different column type, or even maybe the table name has changed. Something significant like that that's going to break that code. Now these two modules are coupled to each other through the database unintentionally. The right way to do that is to use the event bus instead and to lean into or accept the fact that you're going to have eventual consistency. Imagine a scenario, for example, where you're doing a hotel microservice and you have created these different microservices, for example, one that takes reservations, one that's kind of an admin or administration one that's for maintaining issues in the hotel, and one that's for housekeeping or cleaning the rooms in between stays. If you're sharing a data model, so imagine this is an object in your code, and all of these different microservices have referenced that as a shared library and use that same data model. All of those things might logically store in a table or a couple of related tables in the case of the repair history. That's how you would do it in a traditional monolithic application. But now imagine that the 5th microservice team over there looks at the minutes to clean and says, you know, we don't really need that to be a float. That's too much accuracy. We just really need an integer number of minutes to know how long it's going to take. And so they go ahead and change that, and they say, we're the only ones that use this, so that should be fine. Except, whoops, it turns out that if this is a shared data model, those two parts of the application were also using it. If they haven't been updated at the same time, they're going to now have code that points to a database table that doesn't match that type, and they're going to start throwing errors because the other microservice updated. So what's the right way to do this? It's to have each of these applications have their own copy of the room and only maintain the parts of it that they care about. Now, they'll have different parts of this that they will primarily own, and they'll have other parts of it that are just informational copies of data. But this is what it might look like. The reservations would have things like whether the room is occupied, the number of beds that are in that room. Maintenance might have things like the repair history, and housekeeping might have things like how long it takes to clean the room. And then, if some data changes, for example, imagine the admin application is used to create a bunch of new rooms. There's been an addition built to the hotel, and they want to add some new rooms. So they go ahead and create a new room number. That would publish an event to the event bus that would be new room or something like that. And anybody on any of the other services that cares about the new room event would subscribe to that event, and then they would do whatever action they need to do. In this case, probably create a copy of that room in their own data stores. So each of these would create their own, and they would just have basically defaults for any of the other values that haven't been set yet. So that's what it would look like to do it correctly. Number 3 mistake that I see commonly is making microservices that are too big. The best way to avoid making microservices that are too big is to use something called domain-driven design. Anybody in the room familiar with domain-driven design already? Okay, about half of us. So I'm happy to say that if you're quite familiar with it and you feel comfortable using that as a way to figure out things like what's my domain, what's my subdomain, or bounded contexts within this space, you're going to be in really good shape. This is the right tool to use. For those that aren't familiar with it, there's this great book that is an introduction to domain-driven design that I would recommend as a starting point for figuring out where to draw the lines between your services. But I can also give you 2 simple rules that I think will help sum up what this book is trying to say and what domain-driven design accomplishes. Number 1 is that you want to group your functionality into services that share a data model and change together. So that's kind of a rule of thumb. The number 2 rule of thumb is that you want the smallest microservices possible without creating chatty communication between them. Chatty communication means basically a lot of talking between your services. Let me give you an example of that with problem number 4, which is making ones that are too small. Imagine that somebody on your team just attended a conference and they learned about microservices for the first time, and they're very excited about microservices and they want to do that at work with your next application. And they paid pretty good attention in the talks about microservices, but really what they paid attention to is the name microservices. So micro means small, right? So they're like, let's micro the heck out of these services. Let's make them as small as possible. So now, when your users log in, that'll be one service. When your users want to reset their password, that'll be a separate service, and so on and so forth, right? Essentially, one endpoint per service. Well, what happens here? Every time a user logs in, if they fail to log in, you might want to keep track of how many times they failed in a row, how long it's been since they failed last time. And you might want to eventually, after 5 failures, you might want to force them to reset their password or something, right? And then when someone does reset their password, you might want to reset that count back to 0 and have the user log in, have their new password immediately so that they can immediately log in and not have to wait for that to spread between the different microservices. So what's going to happen between these services is every time they do anything, they're going to have to chat with each other, update each other, eventual consistency. This is going to be too chatty of a way to separate your microservices. Even if you use an event bus, unlike this diagram here where I have the arrows going directly, even if you use an event bus, this is not going to be ideal because it's going to take too long, and every single thing that either of these services do is either publishing or subscribing to an event. So really, you're looking for a balance point between having smaller microservices that are very chatty and having bigger microservices that are not chatty at all. If you go all the way to that end, you end up with a monolith, right? If you go all the way to this end, you end up in that silly scenario that I just gave the example of. So if you're looking for that balance and you're looking for things that change together and things that share the same data, that's going to be kind of your basic rules. Problem number 5 is starting from scratch. So many applications that I've seen that are microservices came out of the fact that, hey, we just learned about microservices. The talk that I went to or the YouTube video that I saw said it's the best architecture for everything. And we're starting a new application next week, so let's build it using microservices. There's some advantages to doing an existing project migration from a monolith to microservices. Some of them I've got right here. Number one, if you already have a monolith, you've got all the relationships are defined in the code. What data talks to what other data, what entities are related to each other in the database, et cetera, et cetera. You can actually look at that code. You can see maybe where the lines are between your different services just based on that as documentation. You also have people who know that system, probably people who built that system, who are maintaining it and know it well and can help you decide where to split things up, how to architect things, can understand the history of the application and know why things were done a certain way. You also have a system that already works. Why is that useful? Probably most of us are working on some sort of a deadline. Does anybody have a boss that you can go to and say, we'd like to do microservices and it will take, we don't know how long, is that okay? And he will say yes, or she will say yes. Anybody? No? Me neither. Right? There's always a deadline. So what's great about having a system that's already working? Maybe it's not even working great. Maybe it's a little too slow. It's hard to maintain. It's fragile. But if it's still working, that buys you time. Now you can spend some extra time building the microservices well and not worry so much about, we don't have this feature. The last one is a baseline to compare to. If you have an existing application that you move to microservices, you know whether you've made it better or you know whether you've made it worse because you have data before and data after the migration. There's a couple different approaches when you're migrating an application. Hopefully nobody isn't tempted by this Big Bang approach. This is where you basically get locked into a conference room, told you can come out whenever you've finished the migration. That doesn't work very well. It's not very agile. It might be legally kidnapping. Strangler fig is another pattern that we're going to talk about. That's a really good way to approach gradual migrations. And it's actually based on this plant that actually exists especially in Australia. It starts with a seed that gets dropped by a bird into the canopy of the trees, and it'll start growing down the trees as a vine. It'll eventually reach the ground and sink its vine into the ground and create roots. At that point, it'll start to actually choke out the tree, and the tree will start to not be able to get the nutrients and water that it needs from the ground. Eventually, that tree will die, and it will just be this strangler fig plant that's left over. So kind of a slow motion, violent example from nature, but I think it's a perfect example of what it looks like to gradually migrate an application. If you start out with a legacy application, it's bigger here because it's got most of your functionality in it, and you want to move that to a modern application, but you want to do it in a way that's agile, that actually gets the application out into production as soon as possible. You can start by putting a facade layer in front of it and just have a very small modern application, maybe 1 or 2 endpoints in that application at first, and use that facade layer to make it invisible to your users so that it will seem like they're still hitting the legacy application that they've always used. Gradually over time, you can spend your time moving functionality from the legacy to the modern. Eventually, the modern gets bigger, and the legacy is smaller. And then hopefully, eventually, you reach that point where you've actually moved things over completely to the modern application. You could theoretically get rid of that facade layer at that point. So that's the approach I always recommend if people haven't built a microservices application before, is start with a well-designed monolith. There's an architecture you can use called a modular monolithic architecture that is a lot like microservices and is very easy to migrate to them. And then later, when you actually understand your problem domain a lot better and you've got a working application, then later start trying to figure out where you want to actually make microservices. Problem number 6 is coupling your microservices to each other through your cross-cutting concerns. Cross-cutting concerns are just, if you're not familiar with that term, it's just anything that every part of the application cares about. So examples, security, logging, configuration. These are things that should probably be accessible and shared throughout your entire application. If you're doing a monolith, you would probably write class libraries that would do each of these things, and then that class library would be shared throughout the application. Every part of the application would access configuration the same way, would access security information the same way. but it's hard to do that when you're doing a distributed microservices architecture. So how do you make sure that these things don't end up becoming coupling between your applications? Well, you want to think about finding libraries that do things in these 4 ways. You need things that are distributed by nature. You need things that allow you to be loosely coupled. You want to obviously be fault tolerant, and you need to also be technology agnostic, something that a lot of teams forget about when they're building microservices. I'm assuming there's a lot of .NET developers in the room. If you have 5 microservices in your application, not all 5 of those stacks need to be .NET stacks. There might be one of them that makes more sense to be Java because there's already some logic that's written for that application in Java, or maybe it's interfacing into an application that was written in Java, and it's easier to do that way. Technology agnostic logging, for example, like using the OpenTelemetry standard, is a great way to handle things like this and make sure that all of the parts of the application can log together, and you can go debug things in one place, but still have them be technology agnostic and loosely coupled to each other. Number 7 problem is synchronous communication. This is a very common one. So let me give you an example of this. Imagine you've got an orders service and you've got a customers service. They're separate services. They have separate data stores. So when an order comes in, it'll come in with things like what product is being ordered, what the quantity is, and it'll also come in with a customer ID. Well, you need to go look up that customer ID by going and getting the customer data. Let's imagine you do that as a synchronous call, either through HTTP to the customer application or directly to the customer database, and say, get me customer ID 123. Customer will respond, customer service will respond, you get the customer data, and you can finish processing the order. Well, what happens when the customer team brings the customer service down for maintenance? Now the order service isn't able to work anymore, and the order service is down because that customer ID comes in, it goes off to try and get it, and that service doesn't respond. Now, in the story I told at the beginning of the customer that came to us with the microservices application that was almost ready to deploy but had a performance problem, this is exactly the problem that that application had. Imagine they have all these services with all these references to each other. I've simplified it quite a bit here to give you an idea of what happened. Now, this service right here starts to get busy and it starts to slow down. So it used to respond in 50 milliseconds. Now it's responding in 150 milliseconds. No big deal, right? Application should be fine. These are isolated microservices. Well, guess what? These 3 microservices all call that microservices. So now they take 150 or more milliseconds than they used to as well. And pretty soon, all the ones that call them start to slow down. Now it's more like 300 milliseconds that have been added. And then this last one that, of course, was referencing at least one of those starts to slow down by maybe 400 milliseconds. And round this goes. It becomes basically an avalanche of slowdown, all because one thing started to slow down just a little bit. So are these things truly loosely coupled if this sort of thing happens to them? Of course, the answer is no. They are not loosely coupled. So what are the alternatives to synchronous communication? Well, there's a couple kinds of asynchronous communication. Number 1 would be the service bus, which is the best case scenario. I recommend basically 99% of the time in your microservices architecture, you should be using the services bus to communicate. Another one would be asynchronous polling. So occasionally you need to get something a little faster. You might want to go get it as soon as possible. And maybe it's a system that is an external system that's not able to publish and subscribe to the event bus. If that's the case, then asynchronous polling is a good option. And then the last one is a pattern for synchronous communication between services, which is called the circuit breaker pattern. So if you imagine service A calls service B directly because service B isn't able to respond to events for whatever reason, maybe it's legacy code or code you don't have any control over. Service A calls service B, and service B doesn't respond very quickly. Service A fails that request. The user has to try over. They try again, because of course, anytime something fails in the application, the user is just going to click again, right? They try again. The second time, it also doesn't respond in time. At some point, you would have a circuit breaker flip in your code in service A that says if service B keeps not responding or keeps being slow, then we're going to stop even trying to call it, and we're just going to return an error straight to the user that says that functionality is not available right now. Stop trying to call service B, because by calling it over and over and over again, you're only making things worse if there's something bad going on in service B. So that would be an option for synchronous communication. Problem number 8 is breaking changes to your event contracts. Once you get past most of these other problems, you're going to get to the point where you have a well-defined and a well-designed microservices architecture. This is a problem that really only happens to people once they have a well-defined and designed microservices architecture. Now you've got all these events that are going on between your different services, and oops, now you need to change one. There's a new feature you didn't predict ahead of time. You need to change something. So what do? There's 4 basic rules that I think about for how to change your microservices. Number 1 is that any new required field, you don't add any new required fields, you only add optional fields with default values. Number 2 rule would be any unrecognized fields are ignored but forwarded. So if I receive an event in my microservice, and I say, I've never seen that field before, I don't know what that means, I'm going to just ignore it, but I need to forward it on if I then create another event that says, hey, I received this thing and I did this with it. I need to forward that information on so that other microservices that might know what that means are able to handle it. Number 3, all the consumers of these events need to be aware that optional fields have default values and use those whenever they're missing. So if I receive an event that doesn't have something in it because maybe the service that published that event doesn't know about that new field yet, I need to just go ahead and use the default value. And then number 4 is when you can't satisfy 1 through 3, you create a new event type. Earlier we talked about a sample event that's a new room was created event. I might have a new room created version 2, new room created version 3, etc. And basically, I need to publish, anytime I create a new room, I need to publish all of those events. If there's 3 currently, I need to publish all 3 of those so that anyone who's listening for version 1, 2, or 3 can respond to the event based on that event version. Eventually, hopefully, everyone who's listening to event version 1 will move on to at least 2, and you can get rid of event number 1, but you do need to version it at that point. Problem number 9 is not automating builds and releases. Hopefully this is as surprising to you as it is to me, but so many customers that I talk to who want to build microservices, one of the first questions I'll ask them, of course, is why? Do you have a very good reason for building microservices? But the second question I'll usually ask them is, do you have automated continuous integration and deployment in your environment? When they say no, I always say, well, before we even talk about microservices, you need to get that set up or we can help you do that. The reason why is because the whole purpose of microservices is being able to deploy independently and deploy more frequently and have it be more reliable, less error prone. If you're doing that stuff manually, there's no way you're going to succeed at any of those goals. It's very time consuming and prone to errors to do CI/CD manually. So this is really a prerequisite for microservices. And the last one I want to mention is mismatched teams. This is one that often people don't think about. There's a law that's called Conway's Law. You might have heard it before. Basically says that an organization that designs a system will produce a design whose structure is a copy of the organization's communication structure. What does that mean? It basically means that an engineering team is going to make something that looks an awful lot like the organization's org chart. Example that's often cited for this from the early days of programming when this Conway's Law was first come up with is that if you assign 4 different groups to build a compiler, they will create a 4-pass compiler. Because who's going to say, oh, we didn't realize the other 2 groups did all the parts that we did, you don't need us. go ahead and just do a 3-step compiler. Every group is going to necessarily want to be part of it. So what does that mean for microservices? Well, it means that this structure right here, where there's a single team, maybe 5, 10 people, working on a microservices application, is not a good fit. This doesn't really fit microservices. This fits microservices pretty well. Now, can you switch people between teams? Sure, but probably not every day, not every week. This is going to be pretty stable groups of people who are working on independent applications, almost completely independent of each other, except for some events that they're using to talk to each other. Now, you might have a couple of smaller microservices, and you might have one team that shares those 2 smaller microservices. That can make sense. You don't have to be super strict about this. But if your team looks like one small team, the chances that you're going to even take any advantage of microservices is low, and the chances that you're going to accidentally create coupling between the different microservices is high. So, to sum up a little bit, what have we learned today? We learned that monoliths can be good, hopefully. There's such a thing as a good monolith, a modular monolith. Microservices really only make sense if you have a really good reason, which we talked about a few examples of that. You should really consider starting with a monolith, even if you're thinking, I'd like to go to microservices eventually. If you're building a new application, it really makes a lot more sense to start with a monolith and then eventually migrate it to microservices. Number 4 is that if you have a small single team, microservices are probably not a good fit. If you have lots of independent teams, it might be a good fit. And then finally, if you're going to implement microservices, make sure that you're thinking about these 10 pitfalls that we talked about together today. So with that said, we have about 8 minutes together left, and I want to open things up for anybody who has any questions about anything that we've just talked about. And I believe we'll have a microphone. Is that right? Yes.